Good evening, everybody. Welcome to the Mexborough and Swinton Astronomical Society. We welcome today Dr. Leah Morabito. Born in the United States, she spent 6 years in the US Air Force before earning her PhD from Leiden University in 2016. Subsequently, she was a Hinds Fellow of the University of Oxford before becoming an assistant professor at Durham University. Leah Morabito is a radio astronomer and world-leading expert in high-resolution imaging with the low-frequency array, LOFAR. She investigates how active supermassive black holes in distant galaxies impact the growth of their host galaxies, using specialized data processing techniques she developed for LOFAR to achieve the highest resolution images at low radio frequencies. As a UKRI Future Leaders Fellow, Leah will be using these techniques to conduct the first ever high-resolution radio survey and zoom in on the radio emission from tens of thousands of galaxies to quantify the feedback between supermassive black hole activity and the growth of stars. So please, everybody, put your hand together and give her a good Mexborough and Swinton welcome.
Thank you. I love the silent applause. That's fantastic. And thank you very much, Steve, for that wonderful introduction.
No problem.
I'm very excited. I'm generally really excited to talk about my research, and it's really a pleasure to come and talk to societies like yours, where you're actually interested in listening to me talk about my research. So I hope everyone can see my slides. We tested this, so it should be fine. So today I'm going to talk to you about, as Steve said, about how supermassive black holes impact galaxy evolution. But this talk is a little bit different than I normally give it, because you may have seen recently in the news something about this. So you might have seen this article pop up on the BBC, or you might have indeed caught it on the evening news on August 17th. Astronomers see galaxies in ultra high definition. And this is what I'm going to be talking to you about today. So really what's going on here is that we have new scientific results using LOFAR, the low frequency array, and we'll cover what LOFAR is in a little bit, but I just want to kind of set the framework for what we'll be discussing. So these new scientific results with LOFAR have come from advances in high resolution imaging, and they've driven new science results. The work has really been a team effort from an international collaboration, and much of the work has been led by PhD students. So here on the left, you can see a collection of these new science results. And by the end of the talk, you should be able to tell all of your friends why they're exciting new science results rather than just why they're pretty pictures. So I really want to stress here things that we will highlight in the talk. And so that is LOFAR. So we will cover what LOFAR is and how it works. We will talk about the new science, but I really want to highlight that this has been a team effort and that a lot of the work has been led by PhD students. So I am co-chair of a working group that specializes in high resolution imaging with LOFAR, but a lot of the grunt work is really done by PhD students, and they really should get all the credit for making these very beautiful images. And just so you know, there will be links to all the papers and the media at the end of the talk. So if you want a copy of my slides, I'm happy to provide those for you, and then you can get all the links and go check out all the scientific papers yourself. So in this talk, we will cover two areas. So the first thing that we'll talk about is how we made these images. So I'll give a very brief introduction to what radio interferometry is. We'll talk about the International LOFAR Telescope, and then the advances in high resolution imaging at low frequencies that allowed us to make these really exquisite images. And then in the second part of the talk, we'll come back to the images themselves and talk a little bit about supermassive black holes, so you can understand what's going on in these images, and then the new science results. And we'll finish up by talking about the future plans, which Steve already mentioned is part of my UKRI Future Leaders Fellowship. Okay, so to start off, basic introduction to radio interferometry. So you might have seen this array, the Very Large Array. It's an array of telescopes that is located in New Mexico. I actually got to spend a summer out there once using the array to look at nearby star-forming galaxies, which was quite exciting. It's a very, very beautiful place to visit if you ever get the chance. But one thing I would like to point out here that you probably already know is that the resolution of a telescope is set by both the wavelength you're observing at and the diameter of your telescope. So the bigger your lens, the better resolution you get. And it's the same in the radio, but here we need bigger dishes because now instead of looking at optical wavelengths, which are very short, we're looking at radio wavelengths, which are longer. So we need a bigger dish to collect those longer wavelengths. And you get to a point where you just can't, it's not practical to build a very big dish to get better resolution. And so what we do is a technique called interferometry, where we may build an array of telescopes. And now your resolution is limited by the longest distance or baseline between a pair of antennas in the array. So here you have all these smaller dishes, but they're effectively simulating a much larger telescope and you can get much better resolution. And that's the basic concept of interferometry. This is the only equation in the entire thing, I promise. This is how it all works. So this is the Van Sittert-Zernike theorem, and essentially it's relating the incoming electromagnetic wavefront to how you observe it at the telescopes. So here you have an incoming wavefront, and when you have an interferometer, you know exactly where your telescopes are, you've measured them, you know precisely where they're located, you know precisely where they're pointed, and so you know the entire geometry of this system. And so what you know is if something hits this telescope first, it then has this delay, which you can calculate precisely because you know the geometry of the system, and you know exactly when this wavefront will hit the next telescope. So you can then introduce this time delay into your signal path and essentially line up the wavefront in the back end of your telescope. And you take the voltages that you're measuring from the telescope and you cross multiply them together and you get the coherence of the electric field. And you do this for each pair of antennas in your array. And then we use something called Earth rotation synthesis, which means that you make a measurement with a pair of antennas and each pair of antennas in your array. And the geometry of the system depends on which direction they're pointing at towards whatever you're observing. Well, then the Earth moves a little bit, which gives you a slightly different direction to point at whatever you're looking at. Because we're looking at galaxies very, very far away, which are static against, in the sky, which means that as the Earth moves, our direction to them from the telescopes changes. And so Earth rotation synthesis means that we're just starting to collect different information as the Earth moves, and our direction, our line of sight to the target is moving along with that. So we get more information as the Earth moves, and then we take all of that information on what the incoming electromagnetic field looks like, and we can convert these voltages into an image. So that's the basics of interferometry. I could give an entire talk on interferometry, so if you're interested in this, please let me know afterwards, and I can answer your questions. But for the sake of this talk, we'll kind of move on from all of the technical aspects here. So I thought I'd just give you a different look at what kinds of interferometers there are. So we will focus on the low frequency array in this talk. So this is LOFAR. These are some of the antennas, and this is me for size in an antenna field. So LOFAR looks a little bit different than the very large array because the very large array is made of dishes and LOFAR is made of dipole antennas. And so essentially what you have here is you have this white plastic pipe in the middle. At the top is a low noise amplifier, and this is hooked up to wires, which are very, very hard to see. But I mean, they're essentially wires like you might have on the radio, for the radio in your car. And LOFAR actually operates just above and below the FM radio band. We can't operate at the FM radio band because all we would pick up is the radio stations you get in your car. But we take all of these antennas and we combine them together, and that simulates having a dish. And we'll talk about this in a little bit more detail in a minute. You've already seen the very large array in this talk. So these are both interferometers that I've used, both LOFAR and the very large array. Meerkat is another radio interferometer that I've used that you might have heard about. This is a precursor telescope to the Square Kilometre Array. So MeerKAT is built in South Africa. The Square Kilometre Array is a new upcoming telescope that will kind of take over MeerKAT and also some telescopes in Australia to be the next generation of radio telescopes. And one radio detection system that I have used, and it's kind of similar to an interferometer. The actual technology is very similar. The way it's used is a little bit different. But I did spend 6 years in the Air Force, and I flew on this plane, which is called the AWACS. And this red circle just is circling what is called the passive detection system, which is this cheek on the side of the plane. There's one on the other side as well. And this is essentially a radio telescope that's been strapped onto the plane as kind of an afterthought. And it sits there and listens passively, as the name would suggest, for active emitting things, radars, and things that emit radio signals out there. So it kind of does a little bit of the same thing as interferometry, although it's not quite an interferometer, but the system and the technology, a lot of it is very similar. So I thought I would include it on this slide for fun. So MeerKAT and LOFAR have something in common, and that is they are both pathfinder telescopes for the Square Kilometre Array. So you might have heard a lot about the Square Kilometre Array because although it's located in both South Africa and Australia, the headquarters are actually here in the UK, located at Jodrell Bank near Manchester. And so this is going to be the biggest radio telescope we have ever built. It's a huge collaboration amongst a lot of different countries, and it's really going to start pushing what we know about the early universe. So it's very exciting, and it's a very exciting time to be in radio astronomy as we're building up to the Square Kilometre Array. So I've shown you several different kinds of radio interferometers, but one thing they all have in common, they all have many elements that are spread across large regions. Some of them, like the Very Large Array, can be configurable by moving stations. So the Very Large Array actually has a specially built machine that will go out on rail tracks and pick up an antenna, which can be detached from the pad that it's sitting on, and then move it out to another pad. So you can actually, the VLA actually becomes a bigger telescope at some times and a smaller telescope at others. Not everything is configurable though. That's not a requirement to be a radio interferometer, but it is something that is useful if you have it. But all radio interferometers have a special built correlator or supercomputer to put the signals together. So these supercomputers basically are multiplying voltages together from all of the pairs of antenna from each second that the array is operating. And that's a lot of computation. And so they are specially built to do that very, very efficiently because they're doing one thing and they're doing one thing very, very efficiently, putting all those signals together to then be shipped out to the astronomers so they can process their data. And this is a picture of the WIDAR correlator, which is the correlator for the Very Large Array. So these are the computing racks that are actually putting all the information from those dishes that you saw together. Okay, so let's come back and talk a little bit about the low frequency array, which is the telescope that I primarily use. So this is the LOFAR, what we call super TERP, and a TERP is just a Dutch word for a land that's built up. And you can see that it's been built up around here to keep this water out. So you can see this is a field of different stations of antennas. And there's two kinds of antennas here. The eagle-eyed among you might be able to see these ground screens, which show where the low-band antennas are. So these are the ones that operate just under the FM radio band and really are just very, very simple technology. It's literally a plastic pipe with some wires attached to it. The high-band antenna, which operates just above the FM radio band, is a little bit more fragile. And so it has to be protected. So the actual dipole antenna here, it might be a little hard to see, but this shiny metal bit is the antenna. And then there's another one over here, and then the orthogonal ones for the other polarization direction. But it's all supported in a styrofoam frame that's then covered to keep out the weather, because the Dutch, much like us, don't get very nice weather all year round. And you can see that these are collected into what we call stations. So here is one high band antenna station, here's another, there's more over here. And this collection of stations here is what we call the core of LOFAR. And so each of these stations has something like 96 dipoles, and then the signals from all of those dipoles are combined at the station level, and then each station operates the same way as a dish would operate in an interferometer. The signals from a single station are sent to the correlator, and then the correlator puts everything together. So why do we want to do this at low frequencies in the first place? Why not just use the very large array, which operates at gigahertz frequencies? Well, the thing is that when you go to low frequencies, you can learn new physics. And so here's, so radio emission, first of all, is generally, radio emission is from synchrotron emission. And synchrotron emission is just where you have electrons spiraling around magnetic fields. And because the electron is spiraling, it's turning, and turning is acceleration. And when you have acceleration, you can produce radiation. And so that's where the radio emission comes from. So a typical synchrotron spectrum would just be a straight line here. And this is flux or brightness versus frequency. And a typical synchrotron spectrum, if you just have a straight line here, that means that something is brighter at low frequencies than at high frequencies. So for the LOFAR frequencies, that means that you don't have to build something that's as sensitive or as good as the VLA to be able to see something, because if it is a particular brightness at the VLA frequencies, it's like 10 times brighter for LOFAR. So that's one thing. The other thing is that you can see there's this turnover here, and this turnover can happen for a couple reasons. If you have some other electrons that are running around in front of where your radiation is coming from, those electrons can absorb the radio emission, and you get absorption, and that drops your brightness down. It's like putting something in front of a light bulb. If the electrons that are being produced by spiraling around the magnetic fields are packed too closely, they can even absorb each other. And then you get absorption, self-absorption. And so the light never escapes, the radio light never escapes from the source itself. Another thing is that when you move things out to very high redshift, very far distances, the light gets redshifted as it comes towards us, which means that this entire line moves over, which means that things get fainter at the higher frequencies, but still stay pretty bright at the low frequencies. So we can learn new physics, we can see more distant objects, and we can see things that are typically fainter than what we can just see at high frequencies. So that's why low frequencies are important. But it's quite challenging actually to do imaging at low frequencies. There are lots of different things that we have to handle. The ionosphere, which is the top layer of the atmosphere, has free electrons running around in it, and this really wreaks havoc with the incoming electromagnetic wavefronts. So if you can imagine laying at the bottom of a pool and trying to draw the shape of clouds above you, but somebody is kicking their feet in the water and the water is rippling, that's the same kind of thing that we have to deal with the ionosphere. The field of view is very, very large, which means that bright sources at one edge of the field of view can have a huge impact on your image quality. And it's just hard to image a wide field of view. And then the other thing is that we have really high data rates. We have to combine signals from more than, and this number is very inaccurate, it's up to 110,000 dipoles now. So more than 100,000 dipoles across the entire array. So that means you have really high data rates. You have to worry about getting everything properly timestamped. You have to worry about what's going on at one end of the array versus the other end of the array. And that's just really technically and logistically challenging. So I won't go through all of these, but I did just want to give you a feel for how the ionosphere impacts our observations. So this is a low frequency image made at 74 megahertz with the very large array. It wasn't actually with the dishes. At some point in time, they actually strung up some wire antennas, just kind of like LOFAR, but they just put them up in the VLA at some point, and they did a 74 megahertz survey. So what you're going to see here is 9 different sources. These are all galaxies, so they should be static. They should be in the same place. They should look the same because they should not be moving. They should not change shape or anything because they're just there in the sky. And you can see what happens. They're all in the same field of view. And I think actually I'm going to have to stop share. Let me open the video separately. So you can see that the sources are moving, but they're distant galaxies. They shouldn't be moving. You can see also that they're changing shape, but they're galaxies. They don't change shape. So, and this is not the right video. Okay, can you see the video?
We can.
Okay, great. Okay, so you can see that the sources are moving in different directions and they're changing shape. They should not be doing either of these things. And not only that, all of these are in the exact same field, the exact same observation, but sometimes they're moving in different directions than each other, which means that you then have to do different corrections in one direction in your image than you have to do in another direction in your image. And that's what makes the ionosphere really, really a nasty problem for LOFAR, because we have to make all of these look like static point sources we know that they are. Okay, so let me go back to the presentation. And that is this one. Okay. Right, so that is the biggest problem for LOFAR, but we've kind of figured that out. We've kind of solved it. And this is an image. These are 2 images. They're showing the same part of the sky and looking at the sky before we've done an ionospheric correction, and then looking at that same part after we've done an ionospheric correction. These images have a lower resolution than the high resolution images that we're going to talk about later, but this shows you the difference in what the ionosphere does to our data. Okay, so the International LOFAR Telescope is just what its name says it is. It's international, which means that it has flexible resolution by using different sets of stations. So the image I showed you on the previous slide used just the Dutch stations, which are both the core stations that I showed you in the first image of LOFAR, but then also some longer baselines, including remote Dutch stations. And so the maximum baseline that you get here gives you about 5 arcsecond resolution at 150 megahertz. But there are all of these other stations located across Europe. And if you include all of these in the array, then you can actually get better resolution than you can with adaptive optics using the best optical telescopes on the Earth. So at 150 megahertz, very long wavelengths, you can actually beat adaptive optics with optical telescopes, which is just fantastic. So there's a lot of numbers on this slide, but to give you a kind of a feeling for what the improvement is, going from using just the Dutch stations, which was that first image I showed you after the ionospheric correction, to what you can get with the international stations. I'll just show you this. So this is an image. There's some blobs in here. You may not be able to tell what's going on. If you can, then I mean, wow, you should get a Nobel Award, because this is a very, very blurry image. It's very hard to extract any information in it. If we say that this is an image that's taken with the Dutch stations, and then we move to one taken with the international stations, it's a factor of 20 times improvement in resolution. And all of a sudden you can see that this is my dogs in my backyard. You can see there's 2 dogs, you can see all of their features. You can start doing science with this kind of image because you can see what's going on. And this is exactly the same improvement in resolution we get when we use the international stations versus using just the Dutch stations with our radio images. But combining signals from all of these telescopes across Europe is very challenging. So you're just exacerbating all the problems I mentioned before. Your data volume goes up because you have more stations that you have to deal with. You have to deal with the fact that the clocks may not be synchronized between the different countries. The model, your geometric model of the array, has a lower tolerance for errors, the larger the distance between your antennas. The ionosphere can be even more wildly varying between, for example, Poland and Ireland than it is from one Dutch station to another. You also need calibrator sources. So calibrator sources are what you use to check that you've done the corrections that you do to your data are right. And not everything is a point source, which means that we're no longer looking at very, very simple things, and it's much more difficult to correct your data when you're not looking at simple things. So these are all nasty problems, but I'm here to tell you that we have a way to deal with this. And the way we deal with that is we have made a list of calibrator sources in the sky. And so this is work that's been led by Neil Jackson at the University of Manchester. And we've come up with a specialized strategy to use those calibrator sources to correct our data. And that's what I've specialized in. So rather than going through all the technical details of that, I thought I would just give you a little demonstration using a typical LOFAR observation. So I'll actually take the opportunity here to share another movie. Okay, so this is a movie of a demonstration field that we used for the specialized strategy. And what's happening here is we're panning across the field at the resolution with the Dutch stations, and then we're zooming in to a particular source. This is the radio. This is what this source looks like in visible light, optical light. And then we're going from 6 arc seconds with the Dutch array to the new radio image that we've made. And so here at the very center, that bright knot is the center of the galaxy where there's a supermassive black hole. And then we'll zoom across to another image. And so this is exactly what the specialized strategy that we've developed is doing. We start with our Dutch station, the image that we make with the Dutch stations, which is very wide field. It's lower resolution than what we can get with the full international array. And then we essentially zoom into different sources and we can make high resolution images at that position of those sources. So here's another source. Again, this is a galaxy with a supermassive black hole at the center. And then we'll zoom back out and head on over to another source. And this is really the power of LOFAR, because there are telescopes at higher frequencies that can achieve this kind of resolution, but they have tiny fields of view. So for example, if you use eMerlin, you only see 1, maybe 2 or 3 or handful of sources in the field of view because it's so small. But here with LOFAR, we can observe hundreds to thousands of galaxies in a single observation with high resolution. And that's really the power here of LOFAR, is this combination of this very wide field that you can then zoom in very, very deep on these different galaxies. So this video is available on YouTube, and I have the link at the end of the talk. So we will just stop it here and go back to the talk, which is this one. Okay, so this is that field that I just showed you the video of, but this is it looks a little different. And that's because here I'm just showing you the positions of the sources, which are the gray dots. So those are all of the sources that were in the background of the image, and all of those are distant galaxies. It looks like they might be stars in the video that I showed, but they're not. They're all galaxies. And here we know that the field of view of LOFAR is this blue circle here. This is about 5 square degrees. And then the sources that I was showing you are the ones that are circled in blue, and these are our calibrator sources. And then the pink ones, the pink stars, are what we might want to image, for example. And so the way that the specialized strategy works is that we start off with having done some corrections to our data that we know we're going to have to do, like we correct for the clocks and things like this. And we can do that with using a standard calibrator source. But once we start looking at the data for this particular field, we need to correct the data for this field in this direction to get the ionospheric corrections right. And so we start off with the best calibrator source, and we make an image. We correct the data so that we know that this is right. And then from there, we can take those corrections and apply them to the rest of the data, and then make corrections for the residual ionosphere on top of that. So in different directions, we can correct for the ionosphere in all of these different directions towards other sources. You'll note that we're also imaging some sources that are outside of the field of view. We have much, much less sensitivity here, but we tried it anyway because this is the first time we were doing this. And in this case, we were successful, but we're not always successful, as you can see here. But this source here was much, much fainter, so we had much less signal to noise. So we're not surprised that the corrections in this direction didn't work. So this is the basic idea. We start off with one source and we correct it. We apply those corrections to the field, and then we can further, it's easier and easier to correct for the ionosphere in the other directions once you've already done it once for the field. So just to show you again some of those sources you saw in the video and some of the sources that are on the previous slide. This is the real data. This is using the Dutch stations only, so 6 arcsecond resolution. And here are my dogs again for reference. And you improve the resolution by a factor of 20, and you end up with this. So these are some of the high resolution images. And this is all just from the single field that I've been working on for the past few years to make sure that all of our strategy was going well. To give you a little zoom in on one of these sources and show you really what we're gaining here. So this here is the optical galaxy. This is what you get with the Dutch stations only. And then this is what you get, and this is to zoom in to really show you all the detail of what you get by using the full international array to get these really high resolution images. So all of a sudden you go from having information that there is radio emission to actually being able to see what's going on a sub-galaxy scale. And that's really, really incredible. And that's really what's very exciting about these new imaging techniques. So what are we looking at actually? So this might look a bit like the galaxy on the other side, on the previous slide. And this image was taken at the same frequencies, but this galaxy is much, much larger. So here you can see the size of the Milky Way for comparison. And this is bigger than the galaxy that is hosting it. Very, very large, very bright emission. But when you start zooming in on this, and so this is an image here of this particular galaxy, this is M87, at higher frequencies, you get higher resolution. You can start to see there's a jet here. And then if you zoom in even further, you can start to see the base of the jet here. And if you zoom in even further with the Event Horizon Telescope, you can see the light that is just around the innermost circular orbit, the last stable orbit of light around the supermassive black hole in M87. And so although this galaxy looks kind of similar to the one I just showed you, they have this in common, that the radio emission is being generated by a supermassive black hole. And one of the big questions that I try to answer in my research is, how is that supermassive black hole making those radio jets, and how do those radio jets go out and impact the galaxy in which they live? So to just give you a little bit of a foundation for what an active galactic nucleus is. So an active galactic nucleus is when you have a supermassive black hole and it's active. And when we say active, what we mean is that it's actively feeding on its galaxy. So you have material that's trying to cram down onto the black hole. And this is an artist's depiction of what we think happens. But when you have a black hole at the center and material is trying to get onto it, it can't all get onto it at once. And generally it has some angular momentum. And so just like when you watch water all trying to go down a drain, it can't all go down the drain at the same time. And so it sets up in a swirl trying to go down the drain. And the same kind of thing happens here. You end up with this accretion disk that's rotating around the black hole as material is trying to cram in. This accretion disk gets very hot because you get you have all of this matter and it's trying to cram together. And so it just gets crammed together and more crammed together, and it gets hotter and hotter. And then that emits in the optical and UV. So it's very, very bright. It's very, very small. This is only the central 30 light years approximately of a galaxy. And so this is a very, very small, very bright point source of optical light. And that's actually what we call a quasar now. So above the accretion disk, you have hot gas that emits an X-ray. Surrounding this whole region, you have a dusty torus, and the dusty torus is exactly what it sounds like. It's just a bunch of dust that is in a torus that's surrounding the accretion disk. And this absorbs some of the light coming off of the accretion disk, and then it heats up, and then it emits in the infrared. And then in some cases, you get these relativistic jets, which emit strongly in the radio. And just like M87 in the galaxy I showed you on the previous slide, those are what I'm talking about. So these relativistic jets are producing that large scale radio emission or the small scale radio emission on a subgalactic scale that we see. But this only happens in about 10% of the time. And that's one of the main open questions about supermassive black holes, is why do they only produce these relativistic jets about 10% of the time when they're active? To give you an idea of what that looks like to an observer and not an artist's depiction, this is a galaxy Centaurus A. So this is a compilation of an optical image, but it's been overlaid with the radio in the green. And here you can see that central region where the supermassive black holes lives. You can see the red emission is infrared. You can also see these really beautiful dust lanes in this galaxy. And then the blue is hot gas. And so when that's not the same hot gas as the hot gas just above the corona of the accretion disk, because the accretion disk is something very, very tiny in this central blob. So here you have hot gas that's just associated with a galaxy, and that's where the X-ray in this image is coming from. So how can something so tiny have an impact on the galaxies in which they live? Well, so this is the picture that I showed you beforehand, the artist's depiction where all of this stuff is going on. And this is in the nucleus of the galaxy. And there's ways to get the energy that's being generated here from the gravitational potential of the supermassive black hole. There's ways to get this energy out onto larger scales. And those can either be outflows or jets. And the difference between an outflow and a jet is kind of a fine line. It depends on how directional it is sometimes. Or it could just be radiation. So for example, that accretion disk is radiating very, very brightly, very strongly. And so that radiation can go out and actually change the properties of the gas of the galaxy. So although there's a lot going on in this small region, outflows, jets, and radiation can reach out into the galactic disk and beyond, into the halo of an individual galaxy. And radio jets, large-scale radio jets, can actually push out further than that up into a galaxy cluster. So we know that there's enough energy, and we can see that it pushes out to these different scales and has an impact, can have an impact on galaxy growth. But the details of how this happens are still not known, and that's really what my research tries to answer. And just a note here is that we definitely know that the jets emit in radio and outflows may emit in radio. And this is one of the questions that we hope to answer with high resolution images like those from LOFAR in the future. So the big open questions, just to kind of recap for you, are what links the galaxies and their AGN, their active galactic nuclei, on the small scales, and how and when were the most powerful AGN formed, and how do those AGN evolve to shape the galaxies we see today? So these are very, very broad questions, and we're not going to answer these in this talk. If we could answer these in this talk, I would be out of a job because there would be nothing left for me to do. But I thought I would go through some of the new science of what we've learned from these new high resolution images. So we'll come back to this one which was on, I think, one of my first slides. So this image is of a galaxy called Hercules A. It was made by Roland Timmerman, who's a PhD student in the Netherlands. You can see in the optical image, you can see the massive galaxy that is hosting this, these beautiful radio jets. And you might be able to see there are several arcs here in this radio jet, to the right. And so by making this high resolution image at low frequencies and comparing it to those at higher frequencies, Roland has been able to show that these arcs are from the black hole turning on and off every few 100,000 years. So it turns on and you get something going out, and then it turns off and you kind of like, it stops. And so you end up with a buildup or a deposit of material, and then it turns on again and turns off again, and then you get another buildup of material as it turns off, and then it turns on and it turns off again, and you get another buildup of material. So that's quite exciting. This is a little bit of a different case. This is actually a pair of merging galaxies. So you have galaxy A over here and galaxy B over here. We do know that there is a supermassive black hole in here that has a little bit of an outflow. But in this case, what these observations, these high resolution observations have shown is that these merging galaxies have likely triggered this kind of galaxy-sized wind that's blowing out from this central region. So in this central region here on the left, there's a giant star factory that's surrounded by dust, so we can't see it in the optical, and it's blowing out this material from the center there, which is quite cool. This is another piece of work looking at radio jets. So this is the galaxy here in the optical. This is an image that's made with Dutch LOFAR, so low resolution. And then Pranav has made an image of these new jets. So these are old jets, these big, large scale ones. They're about 13 million years old. And then in the very center here of this galaxy, we can see new jets. And so Pranav has looked at these new jets, which are only 150,000 years old. And he's been able to show that these young jets inside this nearby galaxy are actually interacting with the gas in their galaxy, and so causing some sort of change in the galaxy itself. So Shruti Badul at Manchester has been working on doing gravitational lensing observations. And so gravitational lensing is when you have a galaxy that's in the background, you have something really, really massive in the foreground. And the gravity of this really massive thing actually bends the light of the background object around it. And then when it comes to Earth, instead of seeing one object, you see two, or if it's perfectly aligned, you see an Einstein ring. So you'll just see a ring of light. And so in this case, the blue here is the lensing foreground galaxy. And that's an HST image, so Hubble Space Telescope image. And then the orange here you see is the LOFAR lensed quasar. So really, really quite a cool thing. And so what Shruti has shown is that we can use LOFAR to look at these gravitational lenses to understand very faint distant galaxies and also the lenses themselves. And gravitational lensing is really cool because it doesn't just bend light, it magnifies it. So that means you can see things that you wouldn't necessarily be able to see with your telescope because they're so far away and so faint. But then when the light gets magnified, you can actually see below the sensitivity limit of the telescope itself, which is really cool. So this is a very distant galaxy from when the universe was only a quarter of its age. Again, you have a background optical image, and then this is the new high resolution radio image. And I've worked on this galaxy before, and I worked on it with this PhD student, Fritz Speyen. And what he's been able to show is that the light from this very distant galaxy looks just like the radio light we see from galaxies that are like this in the nearby universe. So that means that the supermassive black holes that in the very early universe are exactly the same as the ones we see today. The holes process that we've built up of how material comes in and tries to get on the black hole and sets up into an accretion disk and has radio jets and shooting out. all of that should operate the exact same in the early universe. But this is just one source. But this source is quite exciting because I imaged this. So all of these images thus far have been with the high band antenna, but I actually imaged this galaxy with the low band antenna, which is a little bit more challenging, but still very worthwhile. And so Fritz was able to use my image and his combined with other images from the very large array to really understand what's going on in this galaxy and be able to tell how old the jets are and things like that. And I have to say that when I made this image here at 54 megahertz, this was the highest resolution image below 100 megahertz. But I'm very happy to say that that record has now been broken by a PhD student at Leiden University. So this is Christian Gruneveld's work, where he's used the low band antenna to look at a collection of sources, a collection of galaxies that have these very large scale radio jets. So this is quite a famous one. Here's the core of the galaxy where the supermassive black hole is, and it's got this jet shooting out. It's very, very pretty. And so Christian is really showing that we can push this down to the very lowest frequencies and use the low band antenna and not just the high band antenna of LOFAR. And that's really exciting and important because we need that information to be able to work out things like the age of the radioplasma, which tell us when the jets started and how old they are. So those are the images from the new science results. And to just kind of summarize that for you, the low frequency radio information that we've gotten is really helping us understand jets and outflows. And we can learn about things like their sleep cycles, how old they are, how they might be interacting with their host galaxies. And that's important to understanding galaxy evolution. But what I've shown you is only a very small collection of sources. So the next question is, well, what about the typical galaxy or the average galaxy? What about an entire population of galaxies? And that's where my work is headed next. So I'm part of the LOFAR 2-meter sky survey. So this is a northern sky survey. We've currently processed about 25% of the sky, which is over 4 million radio sources. This is processing with just the Dutch stations at the moment. And I have another video here. Okay. So in this movie, we're essentially flying through the first part of the LOFAR 2-meter sky survey. So again, this is with just the Dutch array, but all of the radio sources that you see here are galaxies. So each of these little bright points is a distant galaxy. That's the radio emission from a distant galaxy. So these are the galaxies that host active supermassive black holes mostly. And you can see that most of them are just blobs, and that's because with the Dutch stations, we can't actually resolve all of the fine detail. That's why we need the full international array to be able to resolve the detail. But some of them are large enough that you can start to see some structure. You can start to see the radio jets in some of these sources, which is quite exciting. So this movie is also available on YouTube, and you can go there and check it out. It's quite fun. It also has music. I don't know why it has music, because there's no music when we observe. So, I mean, that movie is very impressive, but the actual question, if you stop to think about it, is how did we make a 3-dimensional movie from 2-dimensional images, right? So we take a picture, a radio picture of the sky, which is 2-dimensional, and how do we make it 3-dimensional? And the way we do that is by using the redshifted optical spectra. So you may have heard about the redshift of a galaxy before, and that's essentially saying that something will emit a particular spectrum, which will have absorption lines or emission lines. And as that light travels through the universe to get to us, it becomes stretched a little bit. And it stretches towards the redward. So you get this, what we call redshift, where because the longer wavelengths stretch more than the shorter. And so you get this red shifting. So the spectrum gets stretched out and pulled towards the red. And from that, we can tell how far away a galaxy has been. So we know that there should be a reference line here. If we see that it's moved over here, we know that it's a nearby galaxy. If we see that the reference line has moved over here, we know it's a distant galaxy. And if we see it's moved over here, we know it's a very distant galaxy. But let me point out, this is an optical spectra. And we need the optical spectra and the distance information to work out how much stellar light there is, how many stars are forming, because we can measure the radio all we want, but unless we measure the stars and the stellar light, how do we know if the radio is having an impact on that galaxy? So to be able to link these two things, we need to match the radio to the optical image. And this is actually something that you can help out with if you want, if you have some free time. We have the LOFAR Radio Galaxy Zoo project, which is essentially to take our radio images that we've made from the LOFAR 2-meter sky survey, which is ongoing, and match them with some optical data. So if you're worried about doing it, don't worry, there's a tutorial that walks you through everything you need to know to be able to do this. And you can contribute to this citizen science project and help us be able to get information on all of these radio sources. So just a little plug for the LOFAR Radio Galaxy Zoo project. Okay, so the next steps to kind of extend to large populations of sources and understanding the radio details and all of these sources is my Future Leaders Fellowship project. So with the funding that I've gotten, I've been able to hire a PDRA, Nicole Thomas from South Africa, 2 PhD students, James and Emmy. And we've also hired a software developer to help us out with some of the technical aspects of the project and really optimize our data processing. And so the plan here is that the LOFAR 2-meter sky survey is currently only processing the Dutch stations when it's processing the data, but the data is recorded with all of the stations. And so we will be going back and post-processing everything at high resolution. And so we really have all the data we need to do the first sub-arc second radio sky survey. And so that's what I'll be working on over the next several years. We'll get pretty good coverage of the sky. So the coverage of the sky with the LOFAR 2-meter sky survey, each pointing, and there's just over 3,000 to cover the northern sky, gets you this field of view. At high resolution, you get a slightly smaller field of view, but it's still okay. But the idea is that for each of the 3,000 pointings, we'll essentially repeat what we've done in this first observation and get information on millions of sources over the next few years. Yeah, that's what I just said. Excuse me. Okay, so that brings us to the end of how we made these images and what new science have we learned. And I promised you that there would be links at the end. There's kind of a one-stop shop where they've collected these links if you don't want to, go through the trouble of getting my slides and then clicking through all of them. If you go to astron.nl and then click on their news item for the most detailed ever images of galaxies and scroll all the way down for media, you'll find the links, including a YouTube video from Dr. Becky, if you're interested in watching that, which talks about some of this in more detail. And then there are more links there. So, okay, so I'll end there and happy to take any questions.
Leah, we've got some questions already up on the chat. So, Mike Phillips. Mike, can you unmute yourself, please?
Hi.
Hi, Mike. Do you want to put your question to Leah directly?
Thanks. Yeah, thanks, Paul. Thanks, Leah. Great talk. Really enjoyed it. Fantastic new information. All stuff I didn't know. It was great. So the question is, one of your images of the active galactic nuclei was made up of X-rays, radio, and infrared. Yeah. And as well as the red, green, blue, which you pointed out some regions there. I noticed you got some blends, you got some mixtures like magenta, cyan, and yellow. So you were getting presumably combinations of those different wavelengths. Does that help you to map out what the sources of the origins of those stronger wavelengths are across that region?
Ooh, that's a great question. In some cases, yes, and in some cases, no, because it depends on the emission mechanisms, and they can be linked at different wavelengths. So just like I mentioned in the artist depiction slide of the active galactic nuclei, that you have the accretion disk that's very bright in the optical, and then you have the dusty torus, which absorbs that emission and then re-radiates in the infrared. So when the processes are linked and very close together in space, then you can see correlations between them. And if you know that this is going on, that can help you sort of work out what's going on sometimes. But that's not the case all the time. So, I mean, because the thing is that you have to keep in mind that these are 2D images. And so when things look overlapping, are they really overlapping? And that requires an understanding of the emission mechanisms and the specific situation and the geometry of it. And it can be tricky to pick out what's actually going on. Yeah, it's very challenging, but something that we have to try to do. Yeah, it's a great question.
Thanks. Yeah, I think I was thinking in 2D and I need to think in 3D more. Thank you. I was seeing it too flat. Yeah. Thank you.
Okay,
thanks.
Thanks. Gary Ford, Mid-Kent. Gary, can you give your question, please?
Yeah. Hi, Leah. Fantastic talk. Just echoing what Mike said, loads of things I'd never really understood or heard before. I was impressed by or intrigued by the image you show of the active, the AGN, or was it the supermassive black hole with the arcs that you said represented on-off states?
Mm-hmm.
I was trying to understand again. I don't know if you did explain it, but I was trying to understand how what causes the on-off cycle. And what is the like the period of that cycle? You know, how long is it? Regular or is it irregular? But it's mainly the on-off state. What causes that in the first place?
Right. Okay. So that's two questions.
Yeah.
One of them I can answer, and that one is how often does it happen? And the answer to that is that it's every few thousand years. Every few thousand. Let me just pull up the slide again. So I don't misspeak. It's the PDF has so many beautiful images in there, it takes it forever to load. Oh, there we go. So the answer is that yes, we know how long the cycle is, and I'll give you the exact numbers in just a minute. But the other question, what is causing that? We don't know.
All right.
So it could be that there is right. So here I found it every few 100,000 years. So every few 100,000 years, the black hole is turning on and off, and so you get a jet that turns on and goes out, and then it turns off. And so this material that's kind of like free coasting doesn't have anything to push it anymore. And so it starts to pile up, and that's how you get those arcs. We don't know why the jet turns on and off. It could be that the material that's trying to go down onto the black hole, like maybe you get a large clump of it, and then you don't get some for a while, and then you get more, and then you don't get, but what regulates that and what's actually happening, we're not sure. So.
Okay. Yeah, seems fascinating. The concept of the on-off seems a fascinating concept for me. That's yeah. Thank you.
Mm-hmm.
Okay, Gary. Just talking about that image, one of the jets seemed to show that banding, and the other one didn't. Is that purely down to perspective?
I think part of it is, and part of it might be environment. So I've shared this again so you guys can see the image that we're talking about. So on this side is where you see the arcs, and then on this side you don't. And it can be the perspective, because we think that the radio jets are coming out completely orthogonal to each other, or not orthogonal, but completely in the same axis, but just in different directions. And when that happens, and then you can have it rotated, so the jet coming towards you can look different than the one going away from you. But it could also be that the environment is different on each side of the galaxy. So this is going out well beyond the galaxy, and there is gas out there, even though it's not very dense. And it could be that the gas over here is more dense, and so you end up with like more like knots, and it's more confused, more tangled up. It could be, but I don't know for this particular galaxy the specifics of that.
Okay, thank you for that. Mick Nichols. Mick, can you unmute yourself, please? And can we have your question?
Yeah, we had a speaker a while ago now that mentioned that the black hole in M87 were 40 times the size of our solar system.
Mm-hmm.
Now, my question's in two parts. One, is it that big? And two, if it is, even by black hole standards, that's very, very large. So what would actually make it get that big?
Oh, that's a great question. So the first answer is yes, that is correct. It is that big. And the second answer is, well, okay, so we know that this process of what we call accretion does feed the black hole. And you can get supermassive black holes that merge and make a bigger one. So, I mean, so LIGO has detected, kind of solar mass black holes that are merging, but we expect that supermassive black holes will also merge and get bigger. So how you make something that big is a great question that plagues astronomers, because we actually see supermassive black holes that are that big from very early on in the universe. And so, I mean, we're looking at M87 is quite nearby, which means that it's from late in the universe. It's had a lot of time to kind of grow and evolve and get that big. But the real question is, how do you get black holes that are that big, but very, very early on in the universe? And we don't know the answer to that. So it's a fantastic question.
Thank you.
Mm-hmm.
Okay, Mike. Catherine.
I don't know very much about this, but you might be able to clarify a few points. If you have a charged particle moving along a geodesic in space-time, does it emit synchrotron radiation? And if it doesn't, that means that if you get charged particles orbiting a black hole, then they won't emit synchrotron radiation, so they would be invisible to LOFAR.
Oh, okay, I see. So essentially, you get radiation when you have acceleration. So when you have a synchrotron radiation comes from when you have electrons that are spiraling in a magnetic field. That's like specifically what we call synchrotron radiation. And the synchrotron comes from the fact that there's a particular frequency at which they spiral around the magnetic field, and this particular frequency and radius at which they spiral around the magnetic field produces emission that comes out at radio wavelengths. So if you have a geodesic, so if you have charged particles that are, changing direction, so changing that is acceleration, a change in direction is acceleration. So you would get some kind of radiation, but whether or not that would be at radio frequencies, I don't think is clear to me. I don't think it would come out at radio frequencies. But it would depend on the specifics of the situation.
Okay, thank you.
Okay, Catherine. Peter Lloyd.
Yes, thank you, Leah, for a very, very interesting talk. You often mentioned the age of a jet, and I wondered how you measure the age of a jet.
I'm sorry, Leah, you've gone offline with your audio.
Oh, interesting. I don't know why that happened.
I think that might have been me.
Oh, okay. This is a great question, and this is one that I've spent a lot of time working on. Let me go back to a slide. But essentially, it comes down to the fact that higher energy electrons, and so energy corresponds to frequency. So higher frequency electrons will lose energy faster. So if you think about it, if you run a sprint, you're going to get out of breath a lot quicker than if you run like very, very slow and very steady. And it's the same for electrons. The faster they're moving, the faster they lose energy. And so that means that if you have a population of electrons, they start their synchrotron radiation life, and they have this characteristic power law distribution that I showed you in one of the very first slides. That power law distribution, which is fainter towards the higher frequencies, will start to curve. So you start your higher energy electrons start losing energy faster, and you end up with a curved spectrum. And so by measuring the curvature in a spectrum, in a radio spectrum, we can estimate its age. We have to make some assumptions about the magnetic field, which we can do using other information. I'm not an expert in magnetic field estimations, but this is the general idea. Does that answer your question?
I will have to think about it. But, yeah, I do see what you're saying. And I was wondering during the previous question that synchrotron radiation, the electrons are losing energy and therefore presumably they're spiraling down to standstill eventually. And is that the sort of thing you mean? And how do you know what energy they started?
So we kind of have an idea of what energy they started because we know the mathematics of the situation is actually quite simple. So you have a standard, you have a distribution of particles with a certain energy, and then you introduce them to a magnetic field, and they start. It's all governed by the laws of how they spiral around these magnetic fields to produce the synchrotron radiation. What frequencies they come at, and a distribution of electrons will just kind of have, you can work through all the maths and figure out exactly what you should see.
Thank you.
That's what we're modeling when we figure out how old the populations are. Yeah.
Thank you.
Okay, Peter. Thank you. Jez Robinson. Jez, can you unmute yourself, please?
Should be there now.
Mm-hmm.
Okay.
Yeah, I suppose my question was twofold. Really, was how much are your radio arrays affected by the satellite debris that's up there, as far as all the Starlink satellites and all the extra information gathering devices we've got up there in the sky that weren't going up there when you first started building these arrays? And the second question was, is there ever a future to build a radio array in space? So outside of Earth's orbit, and would that solve a lot of problems or generate a lot more?
Good question. So the answer to the first question is sort of, in that things that are actively emitting radio can be what we call radio frequency interference. So anything that generates a radio signal that is unwanted we just call radio frequency interference. So satellites don't necessarily have the same impact on radio observations as they do on optical telescopes, but sometimes they do emit at specific frequencies, and we just have to block out those channels. The second question about going to space is that actually this has been tried. So the Russians have a what's called radio astron, where they use a radio telescope on the Earth, and then they have a satellite with a radio telescope, and they do interferometry with that, and they can get really excellent resolution, because at the moment we're limited by the radius of the Earth for the resolution of any interferometer. What's maybe more exciting is that there are plans to go to the moon and build on the dark side of the moon, and on the dark side of the moon, you don't have radio frequency interference, or if you do, it's very, very small compared to what we have here on Earth. And you don't have to contend with the ionosphere, so that's absolutely fantastic. That means you can actually go down to lower frequencies, because the ionosphere becomes opaque at about 10 megahertz, and so that's the lower limit of LOFAR's frequency band. But if you go to the moon, you can actually go lower than that, which is interesting for observing the very early universe.
Well, it'll be great for site visits as well. Thank you.
I'm looking for any other questions. Phil Moffitt's waving, but he's going to mention his aerial. So I'm not too sure we should let him
going to mention my aerial. It was
Go
a
on, Phil,
fantastic talk. Really lovely talk. Really enjoyed it. I found the Astron page on Google, which looks really interesting. I don't think I'm smart enough to be able to process the information, but I'll have a look at it. Yeah, just one thing about the jets on black holes. Just like the sun has to emit energy as it's processing what's happening, surely black holes must be doing the same. And perhaps it's only the poles where the excess energy can escape from the black holes as plasma jets out into space.
So black holes absorb material. It doesn't come out, but what is powering all of this is the gravitational potential of the black hole. So the EHT image, for example, that I showed, and it was in the news like a couple of years ago, is actually the light that's on the innermost circular orbit around the black hole. Beyond that, the light cannot come out. So everything that we see, all of the jets and the accretion disk and everything are on our side of the event horizon. But it's all being powered by the immense gravitational potential. So the black hole is so massive, its gravity is so strong, it's pulling things towards it. And the physics of everything that happens around it is happening because of the black hole. Now, black holes have spin and they have mass, and we think these are the parameters that dictate how these systems set up. And so it could be that the jets are coming off of the poles of the black hole, as you say, and that would make sense. But it's incredibly difficult to measure black hole spin. People claim to have done it reliably. Other people claim to have done it reliably, and their measurements don't match at all. Not even 2 sigma different, just completely different. So it's one of the things that we really have to grapple with, because it's really, really tricky to actually know anything about the spin of a black hole. So this is a very good question.
Yeah, really interesting. Top subject.
Thanks.
Thank you, Phil. Leah, I think we've worked you hard enough this evening. So I'd just like to ask everybody to give you a big Max Swinton Astronomical Society thank you. Thank you very much, Leah.
Thank you, and thank you. And I can send along my slides if you're interested in having all the links as well.